Okay, here we are in Math 8, Unit 5, Lesson 4, called Tables, Equations, and Graphs of Functions. So we're still looking at functions today, but now we're going to look at them in terms of having some tables, which we've done before, equations, which we've done before, and we're adding to that some graphing to take a look at functions. Okay, so you began today with a notice and wonder question called doubling back. What do you notice? What do you wonder? And so you had a time to talk about this in class today. And we see here we have distance from the starting line. So how far it is from the starting line is 0, and it goes out to over here, which is about 200 because our intervals of 25. And we notice that, and when you start this in time, they're going out away from the starting line, but as they reach 200, their distance from the starting line begins to go backwards and gets closer, right? And so while we have this, we can sit and wonder how could that be possible? How could they be getting closer? Well, a couple of things could happen here. If you were running on a track, for example, and you start here, right? After you get about halfway around that 200 meters there, once you reach that point of 200 meters, now the further you go here, you start to return to becoming closer to that point, okay? And that's kind of the idea here, okay, possibly what's happening, and we'll look at that a little bit later. Again, starting line with a track, so I'm thinking about a track that goes around in a 400-meter loop there. Let's take a look at the next page, okay? So equations and graphs of functions. It says, the graphs of three functions are shown. So we have a curved one, that's linear one, and another linear one that seems to be going down there. Match one of these equations to each of the graphs. So D, which should be our dependent variable there, equals 60t. We've seen this one before in our last lesson where it was 60 times the time, right? So it was like 60 miles per hour times how long you went, became your distance there. So in this case, it says where d is the distance in miles that you would travel in t hours if you drove, hey, there it is, it's 60 miles per hour. So we saw this same equation before, okay? So time is our independent variable, right? So we're putting into the input of our little box, right? Going in there, we're gonna put our time in there. When we put time in, we come out with the distance. That's our dependent variable. And in this case, our rule is 60 times t. Okay, so which one of these would match 60 times t in terms of like being a number you put in? If I put 0 in there, I'd be at 0 times 60, which is 0. If I put 1 in there, 1 times 60 is 60. If I put 2 in there for t, 2 times 60 is 120. And so when I look here, I can look at this one. I see that it's kind of going up, but that's a little less than zeros there, but 1 should be about 60. Well, no. This one is maybe about 60, and 2 is a little more, 120, right? And so we can see there's a linear approach here. Over here, 1 doesn't quite work. So we would say that this equation seems to match graph B, okay? This is going to be our D equals 60t right there. That's going to match there. All right, so B goes with A, however you want to think about that one. On this one, we have Q equals 50 minus 0.4D, where Q is the number of quarters, had that before, right? And D is the number of dimes in a pile of coins worth 1250, right? So the quarters is our dependent variable, right? And our independent variable, our input, is our number of dimes. But we notice that we're starting at 50 and then we're going down. So when I look at here at choice C, I can see I'm starting at the point 50, and we seem to be decreasing as we go along, right? So as I start, whatever I'm going to start at, I'm going to have a certain number that I'm going to begin at, and then every time I add another dime, I get less and less number of quarters over here. So that's that decrease there. So we start off with a value, and we move our way over. So our quarters here becomes our, well, we'll get there in a second. Sorry, I'm skipping ahead of myself. So we would say this matches C, okay? And this one here, area equals pi r squared, where area is the area square centimeters of a circle with a radius r. We would say that's going to match A here. This becomes our pi r squared equals our area. And over here, Q equals 50 minus 0.4D. Okay. Label each axis with independent and dependent variables and the quantities they represent. So over here, we've already said with our equations before that what we're looking for, the A, that is our dependent variable. The dependent variable we will put on the y-axis right there, and then we'll put our radius, on this case here, being our independent on the x-axis. Over here we're going to put d for distance on this one, and our t for time on the x-axis. And over here these are going to be our quarters, right, our q, and over here this is our d for dimes on this axis there. For each function, what is the output when the input is 1, and what does this tell you about the situation? Label the corresponding point on the graph. Okay, so we want to find the output when the input is 1 for each one of our equations. So let's do the first one. If I have d equals 60t, okay, and I put 1 in there, it's 60 times 1, and so d equals 60. So what does this tell me here? All right, well this tells me that when I have gone for well in this case here, 1 hour, I'm going to travel 60 miles. And that becomes my point on the graph. 1 mile and 60, in one hour I go 60 miles. So if I plot that, I plot it here and say this is at 1, 60. In 1 hour, I've gone 60 miles. With our next equation, we have Q equals 50 minus 0.4D, and we want to put 1 into our input. So our input is here is the D, so we're going to say that Q equals 50 minus 0.4, okay, because times 1 is just going to be what it is. That becomes equal to 49.6, and so Q equals 49.6. So when I have 1 dime, I have 49.6 quarters, is what that means here. So 1 dime is 49.6. I can put that here, 1 comma 49.6. Obviously there's a little bit of problem with that one because, well, can I have 49.6 quarters? Not really. So this one's not going to quite work out cleanly the way it should. And for our last equation, we have area equals pi r squared. We're going to say for our input, we're going to make it 1. So pi times 1 squared, which is 1. So the area equals pi. So our point will be at when the radius is 1, the area is pi. All right, which is about what we say 3.14. So when I look here, I'm going to plug that there at 1. And I'll make that point a 1 comma pi. And now I have marked those there. Now it says to find 2 more input-output pairs. What do they tell you about the situation? Label the corresponding points on the graph. So just real quick, let's just do this one. I'm going to do this one here. If we did 2 more pairs, if I did 60 times 2, I end up with 120. So my coordinate pair would be 2 comma 120. If I did 3, I could do 60 times 3, which is 180. So my coordinate pair would be 3 comma 180. Right, and so I could plot those up along here and do 2 comma 120, and I could do 3 comma 180, right? And that shows me in this case here that it's a linear equation, that it has the same interval as I go from one point to the next. I'm just increasing by 60 each time, and it's linear there. We could do that same thing then for our other equations, and so I'm going to let you do that, or if you haven't done it in class already, that's good. So pick 2 more points here. Again, I would probably pick points that would probably work. When I did the next one here on the Q's, for my D values, I chose 10 and then I chose 20 just to have a little bit nicer numbers to work with. And over here for my R values, I went ahead and just did 2 and I did 3. Those are the ones I used to get myself a couple more points. On the D point, I ended up, when I did the math, 10 comma 46, and I did 20 comma 42. And over here, when I did 2, I ended up with 4 pi. And when I worked with 3, I ended up with 9 pi. So that's what I came up with when I plugged these independent values into the equation up above. But I'll let you work on that on your own. Let's take a look at the next part. Okay, I'm going to bypass the Are You Ready for More real quick and move down to running around the track. So as Kieran was running around the track, the graph shows a time t that he took to run various distances. The table shows his time in seconds after every 3 meters. So here our independent value is our distance. Every 3 meters we're checking the time and seeing where that's going to be. So in this case here, the time that this is our dependent, the time he runs depends on the distance that he's traveled. Okay, that's our dependent variable, and down here this is our independent variable, right? I'm going to input that, and when I input it, I end up with the different times. Now they take this graph and we're going to translate it over into a table like so. So here's what it looks like when I take the points on that graph and plot it out in a table or a chart. Okay, so how long did it take Kieran to run 6 meters? Well, 6 meters is our distance. So when I look across my distance, I find 6. How long did it take? Well, in this case here, we're going to say it took 2 seconds. Now, why did I say seconds? Well, looking back at the graph here real quick, we can see that time is in seconds and the distance is in meters. So just make a note of that real quick in your notes. So it takes 2 seconds to go that far. How far had he gone after 6 seconds? So let's look at our time. We'll look at 6 seconds. How far had he gone? We look there and we can say he had gone 18 meters. Estimate when he had run 19.5 meters. Well, 19.5 meters is somewhere in this range right here, right? It's going to be over here. It's between 6.0 and 6.9, definitely closer to the 6.0 than 6.9, because here I'd have 19 and 20, right? And so it's right in the middle of that there. Well, I shouldn't say definitely closer. Sorry, my mistake. So we have 1, 1, and we're right in the middle of that. So if I found the difference, I could do 6.9 minus 6.0, which is 0.9. And if I divide that by 2, that's going to find me my average there, which is going to be at about 0.45. So I add that back to 6.0, and I end up with 6.45 is where you're going to be at 19.5 meters. I was thinking it was 19, so sorry about that. So at 19.5 meters, we'd be at about 6.5. It takes 6.45 seconds to run 19.5 meters. Again, it is still an estimate. Estimate how far I ran in 4 seconds. Well, here's 3.8, here's 4.6, so the middle of that would be 4.2, which is here, but we're going to be here at 4.0, so we know we're somewhere closer to 12 than 15. If I split the difference between 12 and 15, I know I'm at about 13.5, so I'm less than 13.5 is where I'm going to be. So I can maybe say somewhere around 13, I don't know, maybe 13 meters. Again, it's just an estimate. Where do you think that's going to be? I know at this point it's 13.5, I'm between that and 12. So where is that going to fall? Hard to say. Probably a little less than 13.5, not a big deal. Okay, again, an estimate could be something like, a 12.75. That's kind of what my book says to do. And I can see how you get that, but if you're just estimating, you're pretty close at 13. Is Kieran's time a function of the distance he has run? Explain how you know. So what we're asking is time, the time it takes to run, dependent upon how far he runs, right? So this is our independent value, right? And this is our dependent value. So does the time you put in, does the distance you run determine how long it takes? Okay, and we would say, based on the graph, okay, time is a function of distance. Okay, and we would do that because, and that's because you can look at the distance to see how much time it took to go that far, right? So I can look at the chart of the graph and say, okay, when I look at the distance, it can tell me how long it took to go that far, right? If I look at the distance, I can say, oh, 12 meters. How long did it take? Oh, a little less than 4. 15. Oh, there it is there. So because I can use this is my independent, this determines how long it's going to take there. And that's what we would say there. Okay? Number 2, it says Priya is running around the track. Once around the track. Okay, it's going around the track. The graph shows her time given how far she is from her starting point, like we did in our opening today, right? Here, you go all the way up to 200, and then you start coming back because you're getting close to the starting point there. So what was her farthest distance from the starting point? Well, the farthest distance is going to be located right here at 200 meters, right? We're counting by intervals of 25, so this is 200. Once she gets to the other side of the track, if you start here and you end up there, then you are at, a halfway point of 200 meters. Estimate how long it took her to run around the track. Well, the time in seconds is here. We know it starts at 0 and it ends up here, right about there. We can see we're counting up by, it looks like 12 or so, right? That's a difference there. So if halfway is here, that'd be about 6. So we're halfway between, if this is plus 6, let's make it 78. So we're halfway between 72 and 78, maybe plus 3. Maybe you might say about 75 seconds is what it might take to get around the track, is how fast she was running there. Again, just an estimate there to help us see. Letter C says, estimate when she was 100 meters from her starting point. So for 100 meters, we look here, here's 100 meters from the starting point, and we can estimate that by kind of moving up here, and we can put a dot there and then see about where that's going to be, somewhere in the middle here. So we said before it's about plus 6, so maybe about 18 seconds, right? But notice here, I need to say that it's 18 seconds was where it was at the start of the race, but look at our graph one more time. What do you notice? Where else were we at 100 meters? Right here at this point, which is somewhere at about maybe 48 plus 6, maybe about 54 seconds. It happened twice. So at 2 points in this little race around the track, she was 100 meters away from the starting point. Happens twice there. Keep that in mind. Estimate how far she was from the starting line after 60 seconds. So now we're going to go the other way. We're going to look at 60 seconds. How far away was she? Well, here's 60 seconds. How far away was she? We're going to go across here, find our point, and we're going to look down here. It looks like about 75 meters was about how far away she was from the starting line at 60 seconds. Okay? Is Priya's time a function of her distance from her starting point, and explain how you know? In this case, we would say it is not a function of time. Okay? Is time a function of distance? Meaning, does her time, is it determined by the distance? So let's say, think of it this way. If at 100 meters, whatever I put in my machine, remember my box, if I have an input and a rule, okay, if I put 100 in here and I get out 18, that means there's a rule that's being followed. But notice when I put 100 in here, I got out 18 and I got out 54. I can't have a rule that gives me 2 answers. So when you have this 2 answers for a rule, it means it's not a function. Later on, you'll talk about what's called a vertical line test, right? And if you can see, if I could take a vertical line and it goes through 2 points, then it is not a function. So we would say this one is not a function, and that's because you have a time is not determined by distance. Okay? Time is not determined by distance. We should say distance from the starting line. And that's the big difference here. If this had been a linear race where you just ran that way, then time could be a function of distance. But because we loop back around, it's not going to work out that way. Okay? All right, so that's your idea for today's lesson. Let's take a look at tonight's homework. Okay, tonight's homework, here we go. We have the graph and table shows the high temperatures in the city over a 10-day period. So here's our days, and here's our high temperatures that happen on each of those days. They took that data information and they put it down into a table down below. So let's scoot up here a little bit. It says, what was the high temperature on day 7? So on day 7, our high temperature is here, and it looks like it is 60 degrees. On which days was the high temperature 61 degrees? Well, we're going to find 61, 61, and 61. And notice that happens on day 2, day 4, and day 6. So day 2, 4, and 6. Is the high temperature a function of the day? Meaning, does the day determine the high temperature? Okay. Well, in this case here, we would actually go ahead and say, yes, it works out that way. And that's because on any given day, there is only one high temperature. right? So in a sense, it passes what we call that vertical line test, right? All these things here, there's only one point when you go down vertically. It's not crossing over. If I had another point right here where I said on day 4 there were 2 high temperatures, that's probably not going to be accurate, and it wouldn't be a function, okay? Is the day a function of the high temperature? Explain how you know. In this case, we would say, no, it's not, and that's because, why? Well, because on multiple days, they have multiple high temperatures. So that's why we'd say no for that one right there. All right, I got 5 more minutes to finish my homework here, looks like, before my meeting. All right, number 2. The amount Lynn's sister earns at her part-time job is proportional to the number of hours she works. She earns $9.60 per hour. Write an equation in the form of y equals kx to describe a situation where x represents the hours she works and y is the dollars she earns. Okay, so this is the input. The input is how many hours she works, and the output is going to be, right, the dollars she earns. That's our dependent variable. So what she earns, y, depends upon how many hours she works. Now the rate she's working is $9.6 per every hour. In our case here, our hours is x. Is y a function of x? We would definitely say yes, it is. Okay, and the reason for that is the amount she earns is going to depend on the amount of hours that she works. That's what makes it a function there. So y is a function of x. Next it says write an equation, and you need to write that out in your own words. Write an equation describing x as a function of y. So to do that, we need to move things around. So we would divide 9.6 by both sides, and so we would say that y over 9.6 equals x. And that's how we would make x as a function of y. It would look like that. So be comfortable moving things around there on the equal sign. Number 3, use the equation 2m plus 4s equals 16 to complete the table, then graph the line using s as the dependent variable. Okay, so what we're going to want to do here is we want to put in our numbers. So if m is 0, right, I would do 2 times 0 plus 4s equals 16. And so you have 2 plus 4s equals 16. Subtract 2, subtract 2. So 4s equals 14. What am I doing? Oh, sorry. 2 times 0 is 0. Sorry. Sorry about that. Got in a hurry. Trying to get my meeting. So 0. So 4s equals 16. Divide by 4. S equals 4. And so I put that point right there for s equals 4 on number 3. We're going to follow that same pattern and do your work by plugging in s then for each of these. When you work this out, and your teacher's going to want to see your work, you're going to have 2 and a 5 and an 8. And then your job becomes to plot the points. So 0, 4 is here, 2, 3 is here, -2, which is over here, and 5 is up there. And then at 8, 0, so 8 is over here. We could put that one right there, and there we are. So I plotted that out there, and what I did is I made my m value, I made this my x, and I made this my y. Could I have done the other way? Possibly I could have done the other way, and that would have been something you could have done. One more, and I gotta run. Here we go. We're gonna solve the system of equations. Okay, we're gonna do this with substitution. I know I have a value of y, which is here, so I'm gonna make them equal to each other. I'm going to say 7x plus 10 equals -4x minus 23. I'm going to add 4x to both sides over here, so I have 11x. I'll subtract 10 to both sides here, so that's equal to -33. I'll now divide both sides by 11 to find out that x equals a -3. That's my value of x. Now if I want to find out y, I have to plug that back into an equation. So let's go ahead and we can use this one here. So y equals 7 times -3 plus 10. That becomes -21 plus 10, which is going to be a -11 is what y equals. So now I have a value for x and a value for y. As a coordinate, my solution where those come together is at -3, -11. And that's my solution for that system of equation. That's where the graphs are going to meet, is at that point, -3, 11. That's it for today. Have a great one, and we'll see you next time.